Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this trapezoid ABCD that blocks this circle. In the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing, we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length. This is side DC of trapezoid ABCD. This is equals to 7 over x units in its length. Again, our mission is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again, a trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. Here, side DC is parallel to the opposite side AB. The two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. So DC is the first base and AB is the second base. The base DC, the length of base DC is A, and the length of this the base AB equals to B. And the area of this trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. Again, the area of trapezoid ABCD equals to A plus B times h over 2. The height h, this is the height h, must create 90 degrees with the two bases. And indeed, the height h creates 90 degrees with the base DC, this angle equals 90 degrees, and it creates 90 degrees with the other base AB, because this angle equals to 90 degrees and this angle also equals to 90 degrees. In conclusion, we found out that the area of trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. And the height h must create 90 degrees with the other two bases. Okay. So, first of all, we will define the point of tendencies of this trapezoid ABCD with this circle with letters. We will define the point of tendency of tangent AB with this circle, this point, as E. Likewise, we define the point of tendency of tangent AG. We define the point of tendency of tangent AD with this circle, this point, as F. We define the point of tendency of tangent BC with this circle, this point, as G. And finally, we define the point of tendency of tangent DC with this circle, this point, as H. Here we can implement rule 2. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can definitely implement rule 2 in our drawing. Why? Because in our drawing, we have, this is the common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of this tangent AE as Y, Then the length of this tangent AF must be also equal to y according to rule 2. Likewise, we focus on this common example. Point B. From this common example point B, we have two tangents to this circle, tangent BE and tangent BG, and according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of this tangent BE as Z, then the length of this tangent BG must be also equal to Z according to rule 2. Likewise, we focus on this common standpoint, point C. From this common standpoint, point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to N. And finally, we focus on this common standpoint, point D. From this common standpoint, point D, we have two tangents to this circle, tangent DF and tangent DH. And according to rule 2, they are equal to each other. This is to say, DF equals to DH. So if we define the length of this tangent DF as T, then the length of this tangent DH must be also equal to T according to rule 2. In the next step, we define the length of this side AD of trapezoid ABCD as A. So here, AD, this is side AD, and it is equals to A units according to our definition. Likewise, we define the length of this side BC of trapezoid ABCD as B. So here side BC is equals to B units in its length according to our definition. So what is the value of side AB plus side DC? AB plus DC. Side AB according to rule 2, side AB equals to y plus z. And the opposite side DC, this is side DC, that equals to t plus m according to rule 2. DC in total equals to t plus m. So in total, we actually found out that AB plus DC equals to y plus z plus t plus m. Likewise, we let side AD to the opposite side BC. So what is the value of AD plus BC? Actually, AD according to rule 2 is equals to y plus t. And BC also according to rule 2, it is equals to z plus m. So in total we should find out that AD plus BC equals to y plus t plus z plus m. Here we focus on this expression y plus t plus z plus m. We can change the orders of this expression, the orders of the letters in this expression, according to the algebraic identity that a plus b equals to b plus a. And therefore, this expression that is y plus t plus z plus m will be equal to y plus z plus t plus m. So in conclusion, we found out that AD plus BC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y plus Z plus T plus M. So actually, those two expressions in the green color, they are both equal to the same third expression, that is Y plus Z plus T plus M, and therefore they are equal to each other. That is to say, the expression AB plus DC is equal to the expression DC plus BC. So according to equation 1, we actually found out that AB plus DC equals to DC, AB plus DC equals to AD plus BC. Again, AB plus DC equals to AD plus BC. AB is X, according to what is given as the question, so we substitute AB by X, plus DC. DC is 7 over X, according to what is given as the question. So we substitute DC by 7 over X, and it is equals to AD plus BC. AD is A according to our definition, plus BC. BC is B also according to our definition. So in total, according to equation 1, we actually found out that X plus 7 over X equals to A plus B. X plus 7 over X equals to A plus B according to equation 1. In the next step, we will do a construction, that is to say from point B, we will draw perpendicular on DC. Again, from point B, we will draw perpendicular on DC. So, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC, this point as point S. Actually, by doing this construction, we created here quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because 270 degrees, that is the sum of those three angles, plus the size of this fourth angle, that is 90 degrees, it is 360 degrees, that is the sum of the angles in any quadrilateral. So inside quadrilateral ABSD, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral ABSD, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB equals to X, therefore DS must be also equal to X. According to the same rule, in the same rectangle BSAD, side AD must be equal to the opposite side BS, but AD equals to A, therefore BS must be also equal to A. By doing this construction, we actually created the right green triangle BSC. The right green triangle, triangle BSC, the hypotenuse BC equals to B, side BS equals to A. So what is the length of side SC of the green triangle? From the drawing, it is very easy to see that SC in total equals to DC minus DS. So SC equals to DC minus DS. So I write it down. SC equals to DC minus DS. So SC equals to DC equals to 7 over X, according to what is given as the question, minus DS. We just tried to find out that DS equals to X. So in total, SC equals to 7 over X minus X. SC equals to 7 over X minus X. So in the next step, I'll copy the right green triangle BSC in the new page and we'll implement the Pythagoras theorem on the right green triangle, triangle BSC. Here by PT is the evolution for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the hypotenuse BC of the right green triangle BSC equals to B. Side BS equals to A. And just find out that side BC of the green triangle equals to 7 over X minus X. So actually, this is the right green triangle BSC that I got from the original drawing. According to the Pythagoras theorem, in this right triangle BSC, BC square equals to BS square plus SC square. So I write it down. So BC square equals to BS square plus SC square. This is equation 2. BC is B, therefore BC square is B square. And it is equals to BS square. BS is A, therefore BS square is A square. Plus SC square. SC equals to 7 over X minus X. And therefore SC square equals to 7 over X minus X square. So in conclusion, we shall find out that according to equation 2, B square equals to A square plus 7 over X minus X square. Here we will use the algebraic identity that A minus B square equals to A plus B square minus 4 times A times B. So according to this algebraic identity, we get that the value of this expression 7 over X minus X squared, if we just substitute 7 over X by A and X by B, we get that 7 over X minus X squared be equal to 7 over x plus x squared minus 4 times a is 7 over x, so it is 7 over x times b, that is x. So in this expression we have x in the numerator and x in the denominator, so x will get cancelled. After we cancelled x, we'll have to only minus 4 times 7 in this expression, that is minus 28. So in total, 7 over x minus x squared, according to this algebraic identity, is equals to 7 over x plus x squared minus 28. Therefore, we can substitute 7 over x minus x squared in this equation 2 by this equation, this expression. It is equals to 7 over x plus x squared minus 28. We do it now and we get that according to this equation 2, b squared equals to a squared, and 7 over x minus x squared equals to 7 over x plus x squared minus 28. So according to equation 2, we actually found out that b squared equals to a squared plus 7 over x plus x squared minus 28. So what is the value of this expression, 7 over x plus x squared? According to equation 1, we have already found out that seven over x plus x equals to a plus b. Here, repeat again, according to equation 1, we already found out that 7 over x plus x equals to a plus b. So, if we square this equation 1, we get that 7 over x plus x squared is equals to a plus b squared. Therefore, we can substitute 7 over x plus x squared in this equation 1 by a plus b squared. Okay, we do it now, and we get that according to this equation 2, b squared equals to a squared plus 7 over x plus 7 over x plus x squared. 7 over x plus x squared equals to a plus b squared. So we substitute 7 over x plus x squared by a plus b squared, and according to equation 2 we have to subtract here minus 28. So we subtract here minus 28. So in conclusion we found out that according to equation 2, b squared equals to a squared plus a plus b squared minus 28. So here we'll open the brackets of this expression, and we get that according to equation 2, b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times a times b, and here minus 28. So according to this equation 2, b squared equals to a squared plus a squared is 2a squared plus b squared plus 2ab minus 28. So here we have b squared on both sides of this equation 2, so b square will get cancelled. After cancel b square, in this side of the equation we have with nothing, that is to say 0. On the other side of the equation we have 2x squared plus 2ab minus 28. Here we subtract 28 from this equation, we will add 28 to this equation 2. And we get that 0 plus 28 is 28, and it is equals to 2a squared plus 2ab, and minus 28 plus 28 is 0. So according to equation 2, we actually found out that 28 equals to 2a squared plus 2ab. Here we divide this equation 2 by 2, and we get that according to this equation 2, 28 over 2 is 14, and it is equals to 2a squared over 2 is a squared, and 2ab over 2 is ab. So in total, in conclusion, we should found out that according to equation 2, 14 equals to a squared plus ab. This is according to equation 2. While according to equation 1, we already found out that x plus 7 over x equals to a plus b. So we have here two equations. Our mission is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD will be equal to the sum of its two bases times the height over 2. Repeat again, the area of this trapezoid ABCD will be equal to the sum of its two bases times the height over 2. The two bases must be parallel to each other. Here you can see that side AD is definitely not parallel to side BC. In the next step we will prove that side AB is parallel to the opposite side DC. So why side AB is parallel to the opposite side DC? Because of the fact that ABSD is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC. Again, DS is part of the straight line DC and is parallel to AB. So if a part of the straight line is parallel to the other straight line, then the straight line DC itself must be also parallel to the other straight line, that is AB. In conclusion, we actually found out that side DC is parallel to side AB. And therefore the two bases of this trapezoid ABCD are AB and DC. And the sum of the two bases is equals to AB plus DC. So the area of trapezoid ABCD is equals to the sum of the two bases, that's actually AB plus DC, times the height over 2. The height must create 90 degrees with the two bases. AD, side AD creates 90 degrees with the base AB, this angle equals to 90 degrees, and side AD also creates 90 degrees with the other base DC, because this angle equals to 90 degrees, and therefore side AD is the height of trapezoid ABCD. So this times AD over 2. Repeat again, that the area of trapezoid ABCD in total equals to the sum of its two bases, that is to say AB plus DC times the height, that is AD over 2. According to what is given as the question, side AB equals to x. Likewise, side DC equals to 7 over x. Again, AB equals to x, DC equals to 7 over x times AD. AD, according to our definition, AD equals to A divided by 2. In conclusion, we should found out that the area of trapezoid ABCD equals to x plus 7 over x times A over 2. But according to equation 1, according to equation 1, x plus 7 over x equals to A plus B. Therefore, we can substitute x plus 7 over x in this expression by A plus B. So in total, this expression will be equal to A plus B times A over 2. So the area of trapezoid ABCD equals to A plus B times A over 2. Here we'll open the brackets of this expression. A times A is A squared plus AB over 2. But according to equation 2, A squared plus AB according to equation 2, we already found out that A squared plus AB equals to 14. Therefore, we substitute A squared plus AB in this expression by 14. So in total, this expression after we substitute A squared plus AB by 14, this expression will be equal to 14 over 2. 14 over 2 is 7. So in conclusion, we actually found out that the area of trapezoid ABCD is equals to 7 square units. Repeat again. The area of this trapezoid ABCD equals to 7 square units. We finished with the first question. In the next step, I will present to you the second question. In the second question, our mission is to find out the area of this grand shape. So, in the drawing, we have rectangle ABCD. This is rectangle ABCD. We know that side CB of this rectangle ABCD equals to 7 units in its length. In addition, we know that this is side CP, this is line segment CP, that is equals to 4 units in its length. This is line segment PQ, that is equals to 2 units in its length. And finally, this is line segment QA, that is equals to 5 units in its length. In addition, this is angle CPQ, that is a right angle, and this is angle PQA, that is also a right angle. I repeat again that our mission is to find out the area of this grand shape. So in the first step, we will join point C and A together by a straight line. And we will define the intersection point between diagonal CA of rectangle ABCD with line segment PQ. This point is point M. We will define the length of this. We will define the length of this line segment PM as X. So what is the length of line segment MQ? From the drawing, it it is very easy to see that MQ equals to PQ minus PM. Again, MQ equals to PQ minus PM. Write it down. MQ equals to PQ minus PM. So MQ equals to PQ is 2 according to what is given as the question, minus PM. PM is X according to our definition. So in total, MQ equals to 2 minus X. This is nice at MQ, that is equals to 2 minus X units in its length. By joining point C and A together by straight line, we can adhere two vertex angles. This is angle AMQ, that is defined vertex angle, and the second vertex angle, this is the second vertex angle, that's actually angle CMP. So those two angles are defined as vertex angles, and you know that vertex angles are equal to each other. So if you define the size of this vertex angle AMQ, this angle is theta, then the size of the other vertex angle PMC must be also equal to theta. In the next step, we will focus on this right white triangle AQM. In the right triangle AQM, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing third angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So, the third missing angle must be equal to 90 degrees minus theta. Likewise, according to the same logic, in the green rectangle, the green small right triangle PMC, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus theta. Write it here. The missing third angle equals to 90 degrees minus theta. So in the next step, we prove that those two right triangles are similar to each other. That is to say, we prove that this right white triangle AQM is similar to this right small green triangle PMC. So I write it down. We prove that the right white triangle AMQ is similar to this right green small triangle PMC. So why those two right angles are similar to each other? First of all, those two angles, they are vertex angles and they are equal to each other, or you can say also they are both equal to theta, therefore they are equal to each other. So this is angle AMQ. In the right triangle AMQ, and it is equal to this angle, this is actually angle PMC. In the right green small triangle PMC. Repeat again. Angle AMQ in the right white triangle AMQ equals to angle PMC. In the right green triangle PMC, they are both equal to theta, therefore they are equal to each other. In addition, those two angles, they are both right angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle MQA. The right triangle AMQ, and this is equals to this angle, this is actually angle CPM. In the right green small triangle PMC. So repeat again, angle MQA in the right triangle AMQ is equals to angle CPM in the right green small triangle PMC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, this angle equals to 90 degrees minus theta. Those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. This is angle QAM. In the right triangle AMQ, and it is equals to this angle, this is angle PCM. The right green small triangle PMC. Repeat again. Angle QAM in the right triangle AMQ equals to angle PCM in the right green triangle PMC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the three angles in this right triangle AQM are correspondingly equal to all the three angles in this right green small triangle PMC, and therefore actually proved that those two right triangles are similar to each other according to angle similarity rules. So I will write it down. We actually proved that the right triangle AMQ is similar, this is the sign of similar, to the right green small triangle PMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. That side PM in the right green triangle PMC over side MQ in the right triangle AQM is equals to side PC in the right green small triangle PMC over side AQ in the right triangle AMQ. So I write it down. Repeat again. We conclude that PM over MQ equals to PC over AQ. PM equals to X according to our definition. Over MQ. MQ equals to 2 minus X. And it is equals to PC is 4 over AQ, that is 5. In conclusion, we actually found out that X over 2 minus X equals to 4/5. Here we cross multiply this equation, and we get that 5X equals to 4 times 2 minus X. Here we open the brackets on this side of the equation, and finally we get that 5X equals to 4 times 2, that is 8, minus 4X. Here we add 4x to this equation, and we get that 5x plus 4x is 9x equals to 8. So 9x equals to 8. Here we divide this equation by 9, and finally we get that x equals to 8 over 9, or x equals to 8 ninths. So here 9:07 p.m. is equal to x equals to 8 ninths. We already found out that 9/7 mq equals to 2 minus x. 2 is 18 ninths. Therefore 2 minus x is 18 ninths minus x. And x is 8 ninths. In total 2 minus x is 18 ninths minus 8 ninths. 18 ninths minus 8 ninths is 10 ninths. So in total we should find out that the length of 9/7 mq that's equals to 2 minus x is equals to 10 ninths, while the length of 9/7 pm that's equal to x is equals to 8 ninths. In the next step, I will copy the line AQPC, this line AQPC in a new page, and analyze this line AQPC. Line segment AQ equals to 5 units in its length. Line segment PQ equals to 2 units in its length. Finally, line segment PC equals to 4 units in its length. This is angle AQP, that is a right angle. And this is angle QPC, that is also a right angle. Actually, this is line AQPC that I copied from the original drawing. In the next step, we will extend the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line. So this is a straight line. So if you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle, that is the right angle, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees, according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on the extended AQ. Again, from point C, we will draw perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C, this extended AQ, this point Sn. By doing this construction, we get here quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral PC and Q, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral PC and Q as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PC must be equal to the opposite side QN. But PC is 4, therefore QN must be also equal to 4. Likewise, according to the same rule, in the same rectangle PC and Q, side PQ must be equal to the opposite side CN. But PQ is 2, therefore CN must be also equal to 2. The next step, we join points A and C together by straight line. Repeat again, we join points A and C together by straight line. By joining points A and C, we created the right triangle ACN. The next step, we will implement the Pythagoras theorem on this right triangle ACN. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle ACN, AC square equals to CN square plus AN square. So AC squared, that is the square of the hypotenuse, equals to Cn squared. Cn is 2, therefore Cn squared is 2 squared, that is 4. Plus An squared. An is 5 plus 4. 5 plus 4 is 9. So An squared is 9 squared, that is 81. So in total, AC squared equals to 4 plus 81, that is 85. AC squared, that is the square of the hypotenuse in the right triangle ACN, equals to 85. It has given us the question that ABCD is a rectangle. And you know that all the angles inside any rectangle are right angles. And therefore, this is again ABC, that is a right angle. In the next step, I will copy this right big triangle ABC in a new page, and we will implement the Pythagoras theorem on this big right triangle ABC. Here by PT is the abbreviation for Pythagoras theorem. Side CB equals to 7 units in its length, according to what is given as the question. And we just write down found out that AC square equals to 85. Here AC square equals to 85. So in this right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus CB square. AC square is 85, and it is equals to AB square. AB is the missing side, so we leave it as it is. AB square plus CB square. CB is 7, therefore CB square is 7 squared, that is 49. So here we subtract from this equation 49, and we get that AB square equals to 85 minus 49 is 36. So we found out that AB square equals to 36. We take a root out of this equation, and we get that AB equals to the square root of 36, that is 6. So here This is side AB, that is equals to 6 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the big right triangle ABC. And because of the fact that the area of triangle ABC includes also the area of the right triangle AQM, we have to subtract from the area of triangle ABC the area of this white triangle AQM. This is minus the area of the white triangle AQM, because we are interested only on the green area. So it is the area of the right triangle ABC minus the area of the right triangle AQM. And because of the fact that the area of triangle ABC doesn't include the area of this small right triangle PMC, we have to add to the area of this right triangle ABC the area of this right triangle, right green triangle PMC that doesn't include it in this area of the right triangle ABC. So it is plus the area of the right green small triangle PMC. So in conclusion, we have found out that the area of the green shape equals to the area of the big triangle ABC minus the area of the right triangle AQM plus the area of this small green right triangle PMC. Repeat again. The area of the green shape in total equals to the area of triangle ABC minus the area of the white triangle AQM plus the area of the right green small triangle PMC. So what is the area of the right triangle ABC? The area of this right triangle ABC equals to the base of the triangle, that is AB, times the height, that is BC, over 2. Repeat again, the area of triangle ABC in total it is equals to the base, that is AB, times the height, that is BC, over 2. Minus the area of the white right triangle AQM. What is the area of this white right triangle AQM? It is equals to the base, that is AQ, times the height, that is MQ, over 2. Repeat again, the area of the white right triangle AQM equals to the base, that is AQ, times the height, that is MQ, minus 2, plus the area of the right small triangle PMC. What is the area of this right small triangle PMC? Is equal to the base, that is PC, times the height, that is PM, over 2. Repeat again, the area of the green small right triangle PMC equals to the base, that is PC, times the height that is PM, over 2. So the area of triangle BC equals to AB times BC over 2. AB is 6 times BC, that is 7. BC is 7 over 2. So in total, the area of triangle ABC equals to 6 times 7 over 2 minus the area of the white triangle AQM, that is equals to AQ. AQ is 5 times QM. QM is 10 nines over 2. So in total, we found out that the area of the white right triangle AQM equals to 5 times 10 over 2 times 9, plus the area of the green small right triangle PMC. That is equals to PC. PC is 4 times PM. PM is 8 nines over 2. So in total, we found out that the area of the green small right triangle PMC is equals to 4 times 8 over 2 times 9. So the area of triangle ABC equals to 6 times 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. The area of the triangle is equal to 21 square units. Minus the area of the right triangle, AQM, this is equal to this expression. Here we have 10 over 2 is 5. 5 times 5 is 25. So in total, this expression equals to minus 25 over 9. Plus the area of the right green triangle PMC, that is equals to this expression, 4 times 8 over 2 times 9. 8 over 2 is 4, and 4 times 4 is 16. So in total, this expression equals to plus 16 over 9. So in total, the area of the green shape equals to 21. And here we have minus 25 plus 16 over 9. So it is 21, and minus 25 plus 16 is minus 9. So in total, this expression equals to minus 9 over 9. So it is 21, and minus 9 over 9 is minus 1. 21 minus 1 is 20. So in conclusion, I shall find out that the area of the green shape, is equals to 20 square units. Repeat again, I shall find out that the area of this green shape equals to 20 square units. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our mission was to find out the area of this trapezoid ABCD. So, in the drawing, we have a circle that is described by trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length. Side DC equals to 7 over x units in its length. This is again BAD, that is a right angle, and this is angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again, trapezoid is a quadrilateral with one pair of parallel sides. So here, this is trapezoid ABCD, and side DC is parallel to the opposite side AB. Side DC is defined as the base, and so the two parallel sides are defined as the bases of the trapezoid. So DC is the first base, and AB is the second base. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. So in total, the area of this trapezoid ABCD equals to A plus B times h over 2. Here the height h must create 90 degrees with the two bases. And indeed, you can see here that the height h creates 90 degrees with the base DC, this angle equals to 90 degrees, and it creates 90 degrees with the other base AB, because this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in conclusion, we should find out that the area of this trapezoid ABCD equals to A plus B times h over 2. So, in the first step, we actually defined the point of tendencies of trapezoid ABCD with this circle with letters. We defined the point of tendency of tangent AB with this circle, this point as C. We define the point of tendency of tangent AD, this point as F. We define the point of tendency of tangent AC with this circle, this point as G. And finally, we define the point of tendency of tangent DC with this circle, this point as H. So here we can definitely implement rule 2. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the domain we have a circle, and we also have this common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal. According to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can definitely implement rule 2 in our drawing. Why? Because if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of tangent AE as Y, then the length of tangent AF must be also equal to Y according to rule 2. Likewise, if we focus on this common standpoint point B, from this common standpoint point B, we have two tangents to this circle, tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of tangent BE as Z, then the length of tangent BG must be also equal to Z. Likewise, if we focus on this common standpoint point C, from this common standpoint point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, if we focus on this common standpoint point D, from this common standpoint point D, we have two tangents to this circle, tangent DF and tangent DH. And according to rule 2, they are equal to each other. That is to say, DF equals to DH. So if we define the length of this tangent DF as T, then the length of this tangent DH must be also equal to T according to rule 2. In the next step, we defined the length of side BC of trapezoid ABCD as A, and we define the length of side AD of this trapezoid ABCD as A. And we define the length of side AD as A, and we define the length of this side BC as B. And here we have what is the value of AB plus DC. AB equals to Y plus Z, and DC equals to T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. And what is the value of AD plus BC? AD plus BC. AD equals to Y plus T, and BC equals to Z plus M. So in total, AD plus BC equals to Y plus T plus Z plus M. Here we can change the orders of the letters in this expression according to the rule that A plus B equals to B plus A. Therefore, this expression will be equal to Y plus Z plus T plus M. But AD plus BC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y plus Z plus T plus M. So those two expressions in the green color, they are both equal to the same first expression, that is Y plus Z plus T plus M, and therefore they are equal to each other. That is to say, AB plus DC equals to AD plus BC. AB is X, DC is 7 over X, according to what is given as the equation, and AD is A, and BC is B according to our definition. So in conclusion, actually found out that according to equation 1, X plus 7 over X equals to A plus B. In the next step, we did a construction, that is to say, from point B we drew perpendicular on DC. Again, from point B we drew perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point from point B and DC, this point is point S. By doing this construction, we get the quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABSD we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we write to this quadrilateral as a ABSD as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB is x, therefore DS must be also equal to x. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is 8, therefore BS must be also equal to A. So, by doing this construction, we actually created the green right triangle BSC. In the green right triangle BSC, the hypotenuse BC equals to B, side BS equals to A. So what is the length of side SC of the green triangle? SC, from the domain it is very easy to see that SC in total equals to DC minus DS. Again, SC equals to DC minus DS. DC is 7 over x and DS is x. So in total SC equals to 7 over x minus x. In the next step I copied this right green triangle BSC in a new page and implemented the Pythagoras theorem on this right green triangle BSC. Actually, this is the right green triangle BSC that I copied from the original domain. According to the Pythagoras theorem, this green triangle BSC, according to the Pythagoras theorem, BC square equals to BS square plus SC square. Again, BC square equals to BS square plus SC square. BC is B, therefore BC square is B square, and it equals to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. So according to equation 2, I actually found out that B square equals to 7 over x minus x square. 7 over x minus x square. We have the algebraic identity that a minus b square equals to a plus b square minus 4 times ab. We use this algebraic identity from this expression in the green color, 7 over x minus x square. According to this algebraic identity, the value of this expression 7 over x minus x square, if we just substitute 7 over x by a and x by b, we'll get that 7 over x minus x square will be equal to 7 over x plus x square minus 4 times a, that is 7 over x, times b, that is x. So here we have x in the numerator and x in the denominator, so x will get cancelled. So this expression after we cancel x will be equal to minus 4 times 7 is minus 28. So in total 7 over x minus x square according to this algebraic identity is equal to 7 over x plus x square minus 28. Therefore we can substitute 7 over x minus x square in this equation 2 by 7 over x plus x square minus 28. We did it and found out that according to this equation 2, b square equals to a square, and here we have 7 over x minus x square is equals to 7 over x plus x square minus 28. So in total, according to equation 2, we get that b square equals to a square plus 7 over x plus x square minus 28. So here we have, according to equation 1, 7 over x plus x equals to a plus b. So if we square this equation 1, we get that 7 over x plus x square will be equal to a plus b square. Therefore, this expression 7 over x plus x square in equation 2 will be equal to a plus b square. So we substitute 7 over x plus x square, this expression, by a plus b square. So we did it and found out actually that according to equation 2, b square equals to a square and 7 over x plus x square equals to a plus b square minus 28. And we have minus 28 in equation 2. So we copied minus 28 from the equation 2. So in total, according to equation 2, we actually found out that b square equals to a square plus a plus b square minus 28. So here we open the brackets of this expression, and we found out that b squared equals to, according to equation 2, b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab minus 28. So b squared equals to a squared plus a squared is 2a squared plus b squared plus 2ab minus 28. Here we have b squared on both sides of the equation, so b squared will get cancelled. After cancelled b squared, on this side of the equation we have with nothing, that is to say 0. On the other side of the equation we have 2a squared plus 2ab minus 28. Here we added 28 to this equation, equation 2. We found out that 0 plus 28 is 28. On the other side of the equation we have 2a squared plus 2ab, and 28 plus 28 is 0. So in total, according to equation 2, we found out that 28 equals to 2a squared plus 2ab. Here we divided this equation 2 by 2, and finally found out that 28 over 2 is 14, 2a squared over 2 is a squared, and 2ab over 2 is ab. So in total, according to equation 2, we actually found out that 14 equals to a squared plus ab. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. Repeat again, our mission is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD will be equal to the sum of its two bases times the height over 2. The bases must be parallel to each other. You can see that side AD is definitely not parallel to side BC. But now we prove that side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that we know that ABSD is a rectangle. And we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC and is parallel to AB. So if a part of the straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line that is AB. So in conclusion, we actually found out that DC is parallel to AB. And therefore the two bases in trapezoid ABCD are AB and DC. And the sum of the two bases is AB plus DC. So the area of trapezoid ABCD in total equals to the sum of the two bases, that is AB plus DC, times the height over 2. The height must create 90 degrees with the two bases. Here side AD creates 90 degrees with the base AB, and it creates 90 degrees with the base DC. And therefore AD is the height to the base. So the area of trapezoid ABCD equals to the sum of its two bases, that is to say AB plus DC, times the height, that is AD, over 2. AB is x, DC is 7 over x, according to what is given as the equation. AD is A, according to our definition. So in total, we found out that the area of trapezoid ABCD equals to x plus 7 over x times A over 2. According to equation 1, we have already found out that x plus 7 over x equals to a plus b. Therefore, we can substitute x plus 7 over x in this expression by a plus b. We did it and found out that this expression in total equals to a plus b times a over 2. Here, we open the brackets of this expression. A plus b is a squared plus ab over 2. But a squared plus ab, a squared plus ab according to equation 2 equals to 14. Therefore, we can substitute a squared plus ab in this expression by 14. We did it. So this expression in total will be equal to 14 over 2, that is 7. In conclusion, we actually found out that the area of this trapezoid ABCD equals to 7 square units. In the next step, actually, I presented to you the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side CB of this rectangle ABCD equals to 7 units in length. Inside rectangle ABCD, this is 9/3 CP. This is equals to 7 units in its length. Line segment PQ equals to 2 units in its length. Line segment QA equals to 5 units in its length. This is angle CPA, that is a right angle. This is angle PQA, that is also a right angle. Again, our mission is to find out the area of this green shape. So in the first step, we joined points A and C together by straight line. And then we defined the intersection point of diagonal CA of rectangle ABCD with line segment PQ, this point is point M. We defined the length of PM, of line segment PM as X. So MQ must be equal to PQ minus PM. MQ equals to PQ minus PM. MQ equals to PQ, that is 2, minus PM, that is X according to our definition. So in total, MQ equals to 2 minus X. By doing this construction, we actually created here two vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then the other angle must be also equal to theta, according to the rule that vertex angles are equal to each other. So in the right angle AMQ, this angle equals to theta, this angle equals to 90 degrees, therefore the third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the small green triangle PCM, this angle equals to theta, this angle equals to 90 degrees, and therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we proved that those two right triangles are similar to each other. That is to say, we proved that the right white triangle AQM is similar to the right green small triangle PMC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in this white right triangle MQA are correspondingly equal to all the three angles in this right green small triangle PCM, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two angles are similar to each other, we derive that the following relationship exists between their sides. That side PM in the right triangle PCM over side MQ in the right triangle AQM is equals to side PC in the right triangle PCM or side AQ in the right triangle AQM. Repeat again. We will write that PM over MQ equals to PC over AQ. PM is X, MQ is 2 minus X, PC is 4, AQ is 5. So in conclusion, we found out that X over 2 minus X equals to 4/5. Here we cross multiply this equation and found out that 5x equals to 4 times 2 minus x. Here we open the brackets on this side of the equation and finally found out that 5x equals to 4 times 2, that is 8, minus 4x. Here we added 4x to this equation and finally found out that 5x plus 4x is 9x, so 9x equals to 8. Here we divided this equation by 9 and finally found out that x equals to 8 9ths. X PM is equal to x equals to 8 9ths. MQ equals to 2 minus x. 2 is 18 9ths. So 2 minus x is 18 9ths minus x. X is 8 9ths. So in total 2 minus x equals to 18 9ths minus 8 9ths, that is 10 9ths. So in total MQ equals to 2 minus x, that is 10 9ths, and PM is equal to x equals to 8 9ths. In the next step, I copied line AQPC in a new page and analyze this line AQPC. This is line AQPC that I copied from the original drawing. AQ equals to 5, PQ equals to 2, PC equals to 4. This angle equals to 90 degrees, and this angle also equals to 90 degrees, according to what is given as the question. In the next step, we extended the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line, so this is a straight line. If you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle that is a right angle, and this vicinity angle. So in total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this vicinity angle must be equal to 90 degrees in its size. In the next step, we did reconstruction, that is to say, from point C, we do perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to reconstruction. We define the touching point of the perpendicular from point C and the extended AQ, this point SN. By doing this construction, we created a quadrilateral PC and Q. Inside quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus this, the size of this fourth vicinity angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth vicinity angle must be equal to 90 degrees in size. So inside quadrilateral P, C, and Q, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be a tesseract angle, if not a square. So we relate to this quadrilateral P, C, and Q as a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PC equals to side QN. But PC is 4, therefore QN is also, must be also equal to 4. Likewise, according to the same rule, in the same rectangle PC and Q, side CN must be equal to side PQ. But PQ is 2, therefore CN must be also equal to 2. In the next step, we join points A and C together by straight line. By joining points A and C, we created the right angle ACN. In the next step, we implemented the Pythagoras theorem in the right angle ACN. According to the Pythagoras theorem in the right angle ACN, AC square equals to CN square plus AN square. Again, AC square equals to CN square plus AN square. So AC square equals to CN square. CN is 2, therefore CN square is 2 squared, that is 4. Plus AN square. AN is 5 plus 4, that is 9. Therefore AN square is 9 squared, that is 81. So in total, we actually found out that AC square equals to 4 plus 81, that is 85. So AC square, that is the square of the hypotenuse of the right angle ACN, equals to 85. We know that it is given us the question that ABCD is a rectangle, and we know that all the angles inside any rectangle are right angles. So this angle ABC, is a right angle. In the next step, I copied this big triangle ABC in the new page, and we blended the Pythagoras theorem in this big right angle ABC. This is the right angle ABC that I copied from the original drawing. According to the Pythagoras theorem in the right angle ABC, AC square equals to AB square plus BC square. So AC square is 85, and it is equals to AB square plus BC square. BC is 7, therefore BC square is 7 squared, that is 49. So in conclusion, we actually found out that 85 equals to AB square plus 49. Here we subtract the 49 from this equation, and finally found out that AB square equals to 85 times 49, that is 36. So AB square equals to 36. We took out of this equation and finally found out that AB equals to the square root of 36, that is 6. So this is side AB, that is equals to 6 units in its length. Our mission is to find out the area of this green shape. What is the area of the green shape? The area of the green shape equals to the area of the right big triangle ABC. But because of the fact that the area of this big right triangle ABC includes also the white area, that is the area of the right triangle AQM, we have to subtract the area of the right triangle ABC. We have to subtract from the area of the right triangle ABC the area of the right triangle MQ, because we are interested only on the green area. And because of the fact that the area of triangle ABC does not include the area of this green small triangle PMC, we have to add to the area of triangle ABC the area of this green small right triangle PMC. So in total, we actually found out that the area of the green shape equals to the area of the big right triangle ABC minus the area of the white right triangle AQM plus the area of the right green small triangle PMC. The area of the right triangle ABC equals to the base, that is AB, times the height, that is BC, over 2 minus the area of the white right triangle AQM. This equals to the base, that is AQ, times the height, that is QM, over 2. So it's AQ times QM over 2, plus the area of this right green small triangle PCM. The area of the green small right triangle PCM equals to the base, that is PC, times the height, that is PM, over 2. Repeat again. The area equals to PC times PM over 2. AB 6, BC 7, over 2. So in total, the right triangle ABC equals to 6 times 7 over 2, minus AQ is 5, MQ is 10 ninths divided by 2, plus the area of the green small right triangle PMC is equal to PC is 4, PM is 8 ninths over 2. So the area of the green shape equals to 6 times 7 over 2 is 21. The value of this expression is 25 over 2, and the value of this expression is 16. Actually, the value of this expression equals to minus 25 over 9, and the value of this expression equals to 16 over 9. So in total, we actually found out that the area of the green shape equals to 21, and this expression equals to minus 25 plus 16 over 9. Minus 25 plus 16 is minus 9, so in total this expression equals to minus 9 over 9. So the area of the green shape equals to 21 minus 9 over 9. Minus 9 over 9 is minus 1. So in total the area of the green shape equals to 21 minus 1, that is 20. So in conclusion, we found out that the area of this green shape equals to 20 square units. Okay, thank you very much.